All right. Hello again. For those that weren't there, my name is Jean Lapierre, Senior Director of Advanced Technology at Matrox. I'm also the co-chair of the IPMX activity group for VSF. That's where we write the spec for IPMX. All right, so we'll look at what are the various ingredients in an IPMX network. Okay, so we'll look at things like multicast, dynamic host, configuration protocol, DNSSD, and the NMOS control plane a little bit. When you use PTP, when don't use PTP. We'll look a little bit at the media and control plane design options that we may have with IPMX. We'll look at bandwidth consideration where we're designing a network. And we'll cover also the compatibility of IPMX with SMPTE 2110 and AS67. All right? So the idea is to go over all these things. So these are different elements that you need to consider when you're building an IPMX system, including the network. Some of this you've heard in previous things, but we'll go over them. Okay, so unicast addressing is when packets are sent to the address of the receiver directly. Multicast addressing, well, a multicast address is not the address of the receiver directly. I like to think of them as virtual addresses on your network. Receivers will tell the network, hey, I'd like to receive all the packets that are being sent to this multicast address. Many receivers can join the party. It saves bandwidth and processing. How? Well, if you have a sender doing unicast and it's sending to 20 different receivers, it's going to send 20 times the same packet, one for each receiver. When we have multicast, the sender sends the packet once, and then the switch routes that packet to the 20 receivers that subscribe that. So right away you can see the sender is working a lot less work. It's a lot less work for the sender, and there's less packets on the network. So it's by far the most popular way to deploy IPMX devices on a network. There's many other protocols that use multicast, SMPTE 2110, AS67, NDI, and many more. So we use it when we want a single media stream to be received by multiple receivers. Good example of that, typical Pro AV thing, digital signage around a stadium or an airport, right, where you have like hundreds of monitors displaying the same flow. You don't want the sender to have to send that 100 times. You send it once, it gets distributed by your network. It's great. So, but however, it requires proper configuration of your network, and it's probably, in my opinion, the most complex part of a large Pro AV network configuration. So let's talk a bit about flooding. I'm sure you heard the term. So that's when all the multicast packets are sent to all the ports on the switch, right? So it's actually the default behavior when the multicast traffic is present on the switch and the switch not configured properly for multicast. And most of the time it's undesirable. And so the switch that don't support multicast management, they usually just flood the traffic, because it's actually part of the multicast spec to flood the traffic. And so managed switch, which have multicast support, they have multiple protocols and services that are used to manage the multicast traffic on the switch. Most network switch come out of the box with multicast traffic disabled, because in general, people don't do a lot of multicast traffic, except in our industry when we do multicast, and they will actually flood unless you configure them properly. So what are some of these protocol and services is what we're going to look at now. So the Internet Group Management Protocol, or IGMP, let's do a little quick overview. So there's a join command. So that's when the receiver tells the network that it wants to send all this packet to a given multicast address. The leave is when you tell the network, well, stop sending me all those packets, right? And then there's membership query. That's when the network is asking all the people, all the receivers on the network, like who's still interested in what multicast traffic, and we're going to see what that's used for. First service we're going to look at is IGMP snooping. So IGMP snooping is a service that listens to those IGMP joins message, and it takes note of which port on the switch was requesting, and it programs the routing table to send the requested multicast traffic to that port. It also listens to the leave message, and it takes note of who decided to leave, and then it reprograms the routing table to stop sending the traffic there. But what happens if we forget to send the leave request or we get disconnected from the network? Well, the routing table was going to get fuller and fuller until there's no more place in the routing table, because routing table have a final size in your switches. Different sizes are available. So we need a way to clean up and remove all these useless entries in the table to make space for valid ones. And that's called pruning. And so that's also the job of the snooping process. So how that's done is that there's a timer that the snooping service starts when I do a join to a multicast address. So it starts a timer for my port for that multicast address. And when that timer expires, it basically says, well, clean the entry, removes it. And so if I don't want that to happen, I need a way to reset the timer. And that timer will get reset if I rejoin that stream, okay? And so because of the pruning, the receiver will have to rejoin that stream periodically, otherwise I'll lose the signal. So if the pruning timer is too short and I don't have time to rejoin, I'll lose the signal momentarily. If the pruning timer is set to too long, the table is going to build up, okay? So receiver will have to rejoin periodically at a rate that, is a little bit faster than the pruning timer, and everything will be perfect. And so on the network, if I decide to change that timer, that pruning timer, that would mean I would have to reconfigure all the receiver to join at a different rate, and that's not very practical. And there's another service called IGMP Querier. One of its job is to periodically send an IGMP query to ask receiver to rejoin, basically. So that query message we're talking about, it gets sent, and receiver say, oh, I want to join this stream, this stream, this stream. So the snooping is still listening to those messages, and I'll see those, and it'll reset the timer for everybody that said, hey, I still want this. It'll reset the timer. And if somebody doesn't answer because it got disconnected, well, eventually that timer is going to expire and pruning is going to happen. So we need to set that query timer shorter than the pruning timer. That's one of the things that I see very often. People configure the snooping timer to a number, and then the query is longer than that. And so what happens when you see that is you're going to join, you're going to see the signal, and all of a sudden the signal disappears. What happened? And then it comes back, And it comes back because the querier did a query, your system said, oh, I still need it, but it was too late. It got pruned just before. So what we saw is roughly how that works, and it works pretty well on a single switch or in a single VLAN. But if we have a bigger network, we're going to need to have a way to share the information between all the switches so they cooperate together. For example, I did a little drawing here where I have a client on switch 1 saying, hey, I want something, and that multicast traffic is actually being sent on a port that's on switch 7. So somehow switch 7 needs to realize that somebody wants the signal on switch 1, and also it needs to know that it's going to need to send that traffic to switch 4 and 4 to 3 and 3 to 2 and 2 to 1 type thing. And so all that needs to be coordinated, and there are standard protocols to do that, and then they require well-planned configuration of all your switches. Some manufacturers offer ways to simplify this configuration. They'll have proprietary ways of doing that. And so it can get a little complex when you're trying to mix different brands of switches together to build this multicast network. Next thing I want to look at is Dynamic Host Configuration Protocol, which Stefan mentioned, so DHCP. So when we add a new device to the network, it needs a unique IP address. Every device on the network has a unique IP address. That's the job of the DHCP server, to assign a unique IP address when you request one. And it usually reassigns the same address when I reboot or I disconnect and reconnect type thing, but doesn't necessarily do that, but usually it does. A DHCP address, they have a lease time, so if I connect to a network here today with my laptop, I got an IP address, everything works fine, I disconnect, I never come back, eventually that address will get recycled. There's also kind of a pruning timer for that, and it's called the lease time. So the address can get recycled. That server also provides other useful information, like Stefan mentioned before. The DNS server address is one of that information that's really useful. And to answer somebody's question from earlier, if they're still here, yes, all IPMX device shall support DHCP. It's in the spec. All right, so when we do that tested event, we make sure that every device supports DHCP. However, there are alternatives. If the designer of the system decides not to provide a DHCP server, in general, most devices, when there's no DHCP server but are looking for one, they go to use what we call a linked local address. And that's a self-generated address in the range of 169.254. That is a spec. We didn't invent that. And the device will generate an address, and then it'll check with a standard command on the network if somebody else is using that address. It could happen. And if it does, it picks another one and then just starts again until it finds an address. So that kind of addressing is okay for a very, very small network maybe, but it won't route outside that VLAN or outside that switch, okay? So it won't route, so it's not good. As soon as you have something that's bigger than it's very small, it doesn't work very well. It's mostly useful for temporary setup while doing manual configuration. For example, I take my device, I connect it directly to my laptop. On that cable, obviously there's no DHCP server. My laptop will pick a linked local address, my device will pick a linked local address, and I'll be able to talk to that device and maybe configure it manually to do something specific. So of course, some networks use manual assignment still, and so that would be a way for me to go in my device and set a manual IP address, disconnect it, connect it to the real network. That's how that works. The domain name system, DNS. So it's used to match names like google.com to an IP address. So when you go in your browser and you type google.http Google, it actually figures out what the IP address is for Google, and your device is actually it's going to that address, 172 blah, blah, blah. So it's like a good old phone book, basically. It looks up a name, tells you what the address is. There's another service that comes with DNS, is DNS-SD for service discovery. And that's used to discover services on your network. That's how I like to explain it. So for example, if my computer is connected to the network and you go, hey, scan for printers, what's happening is my computer can ask the DNS-SD, is there any print service on the network? And get back, yeah, there's 3 of them, these are the addresses, and now I can communicate with those printers. And NMOS, as we saw earlier, uses DNS-SD extensively to advertise IS-04 registration and a query. So there's 2 ways to deploy DNS-SD on the network. The preferred way, if you have a well-engineered system or a bigger system, would be to have a DNS server on your network, and a properly configured DNS server with DNS records that expose the DNS server address is published by the DHCP server, like we just saw, sorry. The client would post a request directly to the server saying, hey, I'm looking for this service. Can be more than one server that would answer, that would be listed. And then this will work on your entire network because you got the DNS address server directly, and then it can cover your whole network. The other way is MDNS, or for multicast DNS. So multicast DNS does not require a server. It's done using a predefined multicast address for MDNS. And each client will ask who offers a service, right? And whoever's offering the service can answer and say, hey, I offer this service, and this is where I am. So obviously also there could be more than one server offering a specific service. And MDNS is limited to local subnet only. There's ways to configure switches to do it across subnet, but it's not very common. So IPMX discovery, registration, and query, which I'm going to review again quickly. NMOS devices. I put a new NMOS devices on my network. It uses DNS-SD to discover the IS-4 registration service. It registers with the NMOS registry server it finds with the best priority. And then if no registration service is found, it uses peer-to-peer. i.e. MDNS, to advertise its existence. So I'm a device, I'm a node, I just say, hey, I'm here, I exist, this is who I am. The NMOS controller, on its side, looks for the query service using the NSSD. It uses the one with the best priority it can find. And then if no query service are found, it uses peer-to-peer, and then it goes and finds the individual device, and now it can control those devices directly. I'd say best practice is to use a DHCP server as often as possible, makes things a lot easier. So if you have a small network, so what I'm doing here is looking at what a small network might look like, what a medium-sized network might look like, which service I would put, what do I need to build something. So small network, no DNS server, no NMOS registry, okay? So MDNS is used with peer-to-peer discovery to discover devices. The controller is going to peer-to-peer discover the devices as well. It's going to figure out which ones are sender, which ones are receiver, and connect them as they should. If you have a medium solved, but to medium-sized network, so we're still having a single VLAN here, but there is an NMOS registry. So there's no DNS server to find the registry. However, MDNS, single VLAN, you discover the registry, registration and query. So devices will find the registration, add themselves to the registry, and the ISO5 controller will find the query service, use it, find the devices, and then can talk to the devices to connect them. Have a large network with several VLAN. I'll definitely have an NMOS registry. I'll have a DNS server. The DNSSD service will be there, properly configured. So my NMOS registry will be found by devices using the DNSSD server in the DNS. And again, ISO5 the same way. The controller will find my devices through the query and everything. I want to talk a little bit about NMOS redundancy for the registry. So NMOS service discovery supports having more than one server on your system. You can have lots of servers on your system, and the way you do it is you can assign a priority to each of your servers. So I could have a server with a very high priority and a backup one with a slightly less priority. When the devices look for services, the registration service, they will get these priority associated with each server. And the way the spec works is we pick the one with the highest priority, we attach to it, and if ever that service dies for a reason, we go to the next server priority. And all the devices will react exactly the same way. They will all transition to the other server. And that's the concept of that backup. To PTP or not to PTP. All right, so IPMX sends media stream that are properly synchronized. So if I have an IPMX sender sends an AV stream, the media from that stream, so without PTP, I forgot to mention that. All right, so media streams that are properly synchronized, and that works without PTP, even on very large network, okay? So an IPMX sender can send a media stream to multiple receivers. The audio and video on the receiver will be synchronized to each other, okay? All the receiver will be synchronized within whatever the jitter of the network is. Okay, so if I have 5 receivers receiving the same stream and there's a lot of jitter on my network, yes, the AV on each receiver will be synchronized, but one versus the other will depend on the jitter on the network. They might move a bit. So be interesting if you put all the receivers on the same switch, then they'll experience very similar jitter, and then you can avoid having big difference between your receivers. That level of synchronization is sufficient in most use cases. It's kind of what an HDMI cable can deliver. So if you have a sender and you drive it to multiple monitors, when you're looking at the signal, what's important is that AV sync on that monitor is good, right? And if I have 2 monitors next to each other and they're off by a few microseconds, you won't notice. If they're off by 100 microseconds, which is a few lines of video, maybe, I don't know, 10 lines of video, you're not going to notice. right? So the IPMX makes sure that AV sync is good and the sync between different receiver is competent, I guess, is what I would say. There are use cases where that's not good enough. So for example, if I have a big LED wall that's made up of tiles that are driven by different receiver because each one is a piece and there's different receivers driving it, and at the edge of these tiles, you might notice if there's a discrepancy type thing. So the solution is to put a PTP on your network, everybody's reference to the same PTP, and now my receivers, when they display, they will all display the same pixels at the same, well, not same, the same frame. They will start their frame exactly at the same time because their idea of time will be the same for all of them. Ears are very sensitive to this kind of problem. So if you have speakers, two speakers that are listening to the same source and they're close enough that you hear both of them, if they're not perfectly, if they're not aligned within a certain amount, you're going to notice it, and if they move. So that's another case where you might use PTP, right? And then if you're mixing IPMX devices with 2110 or AS67 device, they're using PTP, so you're going to use PTP at that point. Let's talk a little bit about the media and control. So I'd like to do two quick definitions there so that we're clear. In-band control, that would be when the device with media and control is doing it on the same port, okay, on the same network port. Out-of-band control, my device would have a media port and would have a control port, they're separate. So in-band, same port, out-of-band, different port. So some device can actually do both. And so when to use what depends on several factors. Maybe I'm trying to build a very small network, right, with not lots of connections, so I prefer to use in-band. The cost of the network ports, I'm trying to reduce that. Maybe I'm trying to use the existing infrastructure for my control, and I don't want my media to be on the same network, so I'm going to use out-of-band. You might want to design based on, well, I don't want my media to disrupt the traffic on my control network, especially if my control network's in the existing infrastructure that happens to be my corporate network. I might want to do separate media for that. So sometimes it's a control network can disrupt your media, sometimes it's the reverse. All right, so let's look at what that can look like. For a picture is worth 1,000 words. So I drew here a network switch that has two colors representing the control network versus the media network. All my devices are in-band. They're doing both the purple, which is my media, and the blue, which is my control. And then I have my control devices, my NMOS registry, NMOS controller are blue connections. So in this case, the media can interfere with your control, right? So, but it requires less cabling, less infrastructure, very small network. This might be ideal. When we have a totally out-of-band network here, so I have a blue network, which is all my control, my purple network, which is all my media, and my devices have two connections, one to the control, one to the media. So the media cannot interfere with my control and vice versa, but as you can see, it requires more cabling, more infrastructure, there's more switches. Might enable me though to use my existing corporate network for control and just have a separate network for media. A mixed system, so why? Well, sometimes less cabling makes sense, but you're trying to avoid it. But if I have a big room here with projectors and I have to run the network all the way there, I might want to avoid having to run a cable for control and a cable for media. So a single cable in band may be a good solution. This podium, if I had an encoder here, maybe I want to run a single network cable just to avoid having lots of cable to run it type thing. After all, we're trying to use video over IP to avoid using lots of cabling. So, but maybe the device itself only supports in-band. So that might be another reason why we needed to do this. So I drew this network here where I have a media network, I have the control network like before, but there's a device at the bottom whose control and media is merged together. It's in-band. And so we're going to have to carefully design a connection between our media and our control so that the control can go to the media side to reach that device. And the NMOS registry will need to be reached by that device in order for it to be able to register itself and everything, discovered and all of that. So it's a little bit more complex, but it has its advantages. So the existing corporate infrastructure can be used for control here, but you're going to have to be careful not to let the media into your control network. Cabling is the same as the complex one. It's going to require just as much infrastructure as a non-mix. The media could interfere with control, so it's going to require careful design of that interlink. Let's talk a little bit about bandwidth, which is another consideration when we're building this network. So am I going to use compress or uncompress? I did a little quick math here. We have a UHD P60 signal RGB, like typical graphics. In uncompressed, that's 13 gigabit per second. In a compressed world, this would probably be like for a JPEG XS type of compression, about 800 megabit per second to carry that. So we're going to have to choose equipment depending, obviously. If I'm building something that's uncompressed, I'm going to need 25 gig switches and things like this. If I'm doing compressed, then a gigabit switch is perfect. So choose the equipment based on that, sure. So on a multi-switch network, we need to plan the interconnection properly. So we'll take a little bit of a look at that, because where we connect devices on the network has an impact on our design. So I drew this little network. I'll keep the same network the whole time. I drew this small network, and just to explain, we see TX1, RX1, RX1 there, and one on switch B. That means TX1 is transmitting a signal, and the two receiver next to it is receiving that signal. That's why they're called both RX1. They're receiver receiving signal 1. On switch C, there's a transmitter sending signal 2, and the two RX are receiving it. So my traffic is staying local. I'm using 800 megabit for this explanation. Okay, my traffic is local in my design, so there's not a lot of requirement for my interconnect to deal with that. Now I have a few transmitter on my switch B, and my receivers are on switch C and D. But my workflow is I have this transmitter, and it's going to all these receivers, like this concourse, like this digital signage, all these monitors, for example. And at this moment, my transmitter 1 is sending the signal, and all those receivers are tuned into this transmitter. So there's only 800 megabit of data going through switch A and then being distributed to C and D. So it's a pretty easy thing to do. Now I switch, and now my receiver are receiving transmitter 2. It's still only 800 megabit going across. So if I'm designing something like this, where I have lots of receiver, but they're receiving 1 or 2 sources at a time, the bandwidth requirement for interconnect is not that great. You don't have to go crazy and put 100 gig interconnect in case, apocalypse happened. So I drew another example here where all receivers are on the same switch, right? But now I have lots of transmitters, okay? I have 6 transmitters on switch B and 6 of them on switch C. And all my receivers are receiving these signal on switch D. So my transmitter on B need an interconnect. 4.8 gigabit per second is going into A. And then from C, there's 4.8 gigabit going into A. And then all of that gets added and sent to D. Right? So how you decide to position your devices on your network, and you have to take that in consideration. So you have to plan how much traffic will stay local, how much traffic you plan to be able to distribute somewhere else, right? And you need to provide the connection between these switches accordingly, basically. So, and monitor the connection between the switches just to make sure you don't oversubscribe these interconnection. So now we're going to look a little bit at IPMX versus 2110 and AS67, okay? So the IPMX protocol is based on 2110 and AS67, we saw that. IPMX devices can be added into a 2110 or AS67 network. So when you do that, the IPMX device will use the PTP of your 2110 or AS67 network. 2110 AS67 assume that all the streams are synchronized like we saw before. And IPMX adds support for non-synchronized signals. We saw that as well. So 2110 devices are mostly limited to YUV 422 10-bit support. And IPMX device adds mandatory support for RGB 444 8-bit. So I just wanted to go through the list of like the little bit of a 2110 is this, IPMX is that, so we can go to the next step, which is what does that mean to me if I'm trying to use IPMX inside a 2110 network or an AS67 network. So all IPMX receivers support 2110 and AS67 media stream. Why? Well, they work with PTP, they support PTP network, and they all support YUV and RGB, and they all support uncompressed audio, the PCM, which is AS67, because they're based on AS67. So if I put my IPMX receiver in my network and I send it the 2110 signal, that signal is going to be synchronized, and it's going to be likely YUV 422 10-bit, which I have to support. And a synchronized signal is a subset of is a special case of an asynchronous signal, so we can receive it, no problem. Now there's some 2110 and AS67 receiver that support non-synchronized media stream. They don't care if you're synchronized perfectly to the 2110, to the PTP, even though the spec says you must be. You'll get a receiver that, for example, multi-viewer. Multi-viewer are often like they just get the packets in, they put the image there and they display it when they want type thing, because their output is not necessarily synchronized. So they'll work. There's other examples. There actually are some 2110 receiver that support RGB, because the 2110 spec says everything how to do YUV, everything how to do RGB, and in broadcast they mostly don't use RGB and they're mostly YUV, but 2110 is used in Pro AV today for doing different things, and there are RGB signals out there, and therefore there's receivers that support it. There are some IPMX transmitters that actually send a synchronized stream, like I explained. If you feed me a synchronized signal, I'm going to output the synchronized signal, therefore it's going to be 2110 compliant. If my media player is locked to the PTP, like I explained before, that's a synthetic sender. It'll send a signal that's synchronized and therefore fully compatible. And there's actually some IPMX transmitter that can convert non-synchronized signal into synchronized signal. And so, I made a little drawing and put little devices in them so we can see, so we can illustrate this case. So now what I have is I have a network with a PTP clock, okay? So it's a 2110 or AS67 network. I have this camera and I ran a little line to it because that camera is actually synchronized to PTP. So it's the kind of signal that a 2110 encoder would receive, okay? And so this signal, if I send it to this 2110 transmitter, generates a signal. It's going to be received by that 2110 signal, guaranteed, display an image, so will the IPMX device, receiver. That same signal, I'm feeding it to my TX2 here, which is an IPMX receiver, but it's a synchronous input signal, therefore, my IPMX signal will be, of course, will work with my RX2, which is IPMX, but it'll also work with the 2110 signal because it's why and how we designed IPMX to be based on 2110, generates something synchronized. My blue transmitter here is a gateway that's connected to a computer, like a laptop or something. So it's receiving RGB, okay? And it's generating an asynchronous RGB signal on my network. It's definitely gonna work with my IPMX receiver. And I put a question mark on the 2110 receiver, because if that 2110 receiver supports RGB and also doesn't care about the synchronous, it will work. We actually have a 2110 mixer in the Ames booth that actually does that, so that actually works properly. And I can send it 2110 or IPMX, and it's super happy. And it's not an IPMX device, it's a 2110 guy. And my last line here is that example of that media player that is playing an IPMX signal, but because it's locked to PTP, it's generating a synchronous signal, and it works. It's going to work with the 2110 just as well as it will work with the IPMX. So I just thought it was interesting to review a little bit because of how IPMX is based on 2110 and AS67. This is the kind of thing you can expect for things to work. The only example I didn't put here is one that would take your an asynchronous signal and turn it into a synchronous signal, even though it wasn't a synthetic sender. All right, that's it. Any question? Yes?
Regarding the DHCP requirements for IPMX device, if when the device has two network ports, one for media stream and the other for control, both of them needs to be DHCP capable?
Yes. All network port on an IPMX device must support DHCP.
Thank you.
Yes?
Will there be any guidance on the IPMX standards for setting multicast addresses used?
All right, that's a cool question. In TR10-9, we specify a scheme for selecting the default multicast IP address. Okay, and it's based on the IPv4 address the device got for that port. Okay, and so that means if I take a whole bunch of IPMX devices, I connect them to my network with DHCP, and I can just right there start transmitting and receiving, and there'll be no collision between any multicast address.
It's a bold statement.
It's been tested for years and years, because the scheme we're using is a scheme that the industry's been using for quite a while, actually. So we just wrote it into the spec. And you notice I said the default multicast address. So, of course, you can change it, you can push it with NMOS, you can do what you want, but the default one out of the box. So the way it works is pretty simple. The scheme that we tell people to use is 239 dot the stream number dot the last two digits of your IPv4 address. So the chance that it's going to, in a normal network, a local network, you're supposed to use 192.168 something. Something is the last two IP address, the last two digits of the multicast address, which is full in multicast. The one address that, the one segment where you only get 127 unique value is where we put the stream ID.
Does that imply that you're using the same multicast for video and audio?
So stream number. So if my device on this port transmit audio and video, I'm going to do 0 and 1 for that second digit. 239.0 for my video, 239.1 for my audio. If my address is 192.168.10.10, I'm going to do 239.0.10.10, 239.1.10.10. So my device can send up to 127 different flows, different multicast address without colliding with everybody else. That's the default value. That's why the bold statement. Any other question?
Yes, how do you work on IPv6 interoperability with the control plane?
So IPv6 is, I guess, I can't remember how it's written. It's optional, I guess. It says you have to do IPv4 and you should support IPv6. Yeah, I think that's what it was, right? And we have done experiment with IPv6 and stuff, and it works well, but the device has to support it.
Yeah, and you're not doing anything on the multicast side with MLD, it's just purely IPv6.
Yeah, we didn't write in anything because we don't have a lot of experience right now with the multicast on IPv6. But I mean, the specs that we have, they're very flexible. We can add stuff as we develop type thing. So we do revision and everything. The VSF is extremely agile for doing that. Other question?
Is IGMP version 3 mandated, or is it version 2 or 3?
The IGMP? So the IGMP is like TR 1001-1. We mandate V3, but also V2 support. because in Pro EV, there's a lot of switches that are layer 2 and are V2, right? So right now, the TR10-9 says you should default to V2 and offer an option to do V3, but we went to the interrupt, we did some tests, we had some discussion, this is a part that might change. The issue is there's some switch that, how should I say, they go to V2 if anybody talks V2, and to get out of there is a little bit complicated. So we have in our TR10-9 a thing that says you must let the user set it to V2 or V3, right? And I believe it says default V2, but not sure. I think it is, yes. But both of them are mandated. So there's no IPMX device that does not support V3.
Yeah, I
Yes.
know some of the optional profiles settings were for encryption, for PEP encryption.
Yes.
Is that kind of fully polished, or is that adopted?
It's published,
Yeah.
okay? We keep talking about it, we didn't explain it, but it's really interesting. There's a lot of people that are very interested in it type thing, and even outside of IPMX. What it lets us do, right, is install keys on a transmitter and a receiver, and then they will exchange any media between the two and it'll be encrypted. What's really cool is because it's IPMX and it's published, you can use it for anything you want. And also because the way it's published, documented and everything, I can send from a matrix to somebody else's company, do the encryption and it works. It's the same for the DHCP. It doesn't need to be the same company on both ends. And the way they're written, they can be used, like you could do a 2110 PEP transmitter receiver if you wanted, and it would work. And I'd be able from IPMX to send it to 2110 and the reverse.
I understand it's published. Is it adopted now? Is there interoperability in the kind of initial IPMX devices? Do the matrix devices support that?
Yeah, well, we're in the process of doing all these tests and interrupt, right? And we haven't done that interrupt for PEP yet, but we did do it for HDCP, and so there's different adapter and it works intercompany. And you know, PEP is the PEP spec is based on how we do it. The difference is with HDCP, the keys are the HDCP keys and everything. So we just came up with a different way of installing keys in the system, and there's no key exchange basically, but the encryption is exactly the same. So anybody that does HDCP can do PEP like this, or vice versa.
Yes, sorry to keep asking. Will you be mandating the support for secure mode across all the best practice security? Because most broadcast systems, I've seen many devices that don't support it at all, but certainly most systems don't.
Currently, it's not mandated, but you know, like I said, it's open, so we'll be evolving. So right now, it's not mandated. No.
Would that become a profile that is right, like a secure IPMX profile, where you define the endpoints?
We could do that, absolutely. What's important, okay, is IPMX, VSF, the VSF spec is about the transport, okay? And we did go a little out of our way. We said, yeah, you know what, we're going to spec NMOS for control because, you know, that's important, but that's where we stop. But IPMX belongs to the AIMS, not VSF. So AIMS can easily say, I make a profile and it's TR10 for this, for this, for this, and for that, like, they could even say, like, in this profile, you know, like, this is, I know it's written in the TR10 spec, but for this profile, you can ignore it. Or you could say, I know it says that this TR10 is optional, but we enforce it, right? That's the profile.
I think from a user's perspective in security, because it's such a poor adoption generally, it would be really helpful to have a secure profile.
So that's something for the IPMX, for AIMS would be able to specify and say, here's that IPMX logo. That means the device supports secure type thing, right? Because the specs exist, so they can point to those specs already. We're not trying to do everything in the VSF TR10 spec. We're just putting all the building blocks, and somebody says, these are the Lego pieces that you need in order to get this step. Other question? Cool. Well, we're going to be in the AIMS booth the rest of the week, so if something come up, you can come see us. Thank you.